And for a row and column vector, these guys have to be the same. So for example, if R is 1, 2, 3, and C is, how about just 1, 2, then RC is undefined because I have 3 guys in R, but I only have 2 guys in C. So if I was trying to use my definition of multiplication, I would have to pair up 1 and 1, 2 and 2, and I have nothing to pair 3 up with. So like, what do I do with the 3? We just say it's we just throw up our hands and say undefined because there's nothing to pair it up with. So it only makes sense to multiply 2 of these if they have the same number of entries. Okay, cool. So now we want to think about multiplying 2 just matrices, not necessarily row vectors or column vectors. And we're going to use what we just developed for row vectors and column vectors to define matrix multiplication for a more general matrix. Okay, so let's see how that's going to work. Basically, the way it's going to work is we're just going to do row times column over and over again. So multiplying general matrices, not just columns and rows. Here's the idea is, okay, here's the idea. If A and B are matrices, we're just going to multiply rows of A with columns of B. Matrices have rows and columns. If I want to multiply A times B, what I'm going to do is take the rows of A and multiply them with the columns of B. And that's basically all I'm going to do. So we're just going to kind of do this row times column over and over again to get the numbers for the resulting matrix. Okay, so I think I'm probably, yeah, I don't think I want to write the abstract definition of matrix multiplication on the board for you. I think I'm just going to end up muddling everything if I do that. So I think what I'm going to do is just give a bunch of examples. And if you really want to see an abstract definition, look in your book, and there'll be one in there. I think it's going to be better if I just show you some examples and sort of explain the process as we go, because the process is basically the same for any pair of matrices where this makes sense. So we're going to show examples, and we'll flesh out what I mean by this through these examples. So let's start with a small example. We're going to take this matrix. Someone's ringing my doorbell. I think I'm just going to ignore it. All right. So we're going to start with a small example. I have two 2x2 matrices. Yeah. Maybe this one is A and this one is B, whatever. So to multiply these, our idea is I want to take the rows of A and multiply with the columns of B. So what do I really mean? Maybe I'll grab colors that might be helpful here, just to illustrate what I'm talking about. It means that I'm going to systematically take this row and multiply it by this column, and I'm going to take this row and multiply by this column, and I'm going to take this row and multiply by this column, I'm going to take this row and multiply by this column. We're just going to take all the rows and multiply them by all the columns. And the only question is, where am I going to put my results? Well, I really want to fill in a new matrix. Yeah. And I'll talk a little bit about in a second about how to know how big this new matrix should be. For now, let's just say I have two 2x2s. Maybe the result will be a 2x2. And it turns out that's right. And so here's how this works. If I want to know what goes in the first row, first column of my result matrix, then what I'm going to do is take, so to figure out what goes here, I'm going to take the first row times the first column, because this entry is the first row and first column of the new matrix. So I take the first row of the guy on the left times the first column of the dude on the right. How does that work? Well, this is just a row times a column, so now we know how this works. I take 1 times -1, which is -1, and I add it to 2 times -2, which is -4. So -1 plus -4 is -5. So this entry must be -5. Okay. Now, if I want to go here in the in the first row, second column, I'm going to still use the first row, but now I'm going to multiply it by the second column. So I take this first row, 1, 2, and multiply it by the second column, 0, 3. So 1 times 0 is 0, and 2 times 3 is 6. If I add those together, I get 6. Okay. And so we keep going like this. Maybe I'll do one more of these in color before it gets too messy. Down here, I'm in the second row, first column. So I'm going to take second row times first column. And what does that give me? Well, 3 times -1 is -3, and 4 times -2 is -8. -3 plus -8 is -11. There's my next entry. And then lastly, to go here, this is second row, second column, so I take second row times second column. 3 times 0 is 0. 4 times 3 is 12. I get 12. So here is my new matrix. This would be A times B, this guy here. So again, all we did was take rows of the guy on the left times columns of the thing on the right. So notice that order matters. Rows on the left, columns. That is very important, that you're taking the rows of the thing on the left times columns of the thing on the right. That's very important. If you get that backwards, you will get a completely different answer. So be very careful. Rows on the left, columns on the right. Okay, cool. So maybe I'll write down a little bit more now in general of how this is working again, and then we will do a couple more examples, show you how this is working. So sort of to summarize the procedure. Summary of matrix multiplication. It goes like this. So if A is m by n and B is, I guess we'll just do n by, I don't know, it's another L perhaps. So if I have these two matrices with these dimensions, then we multiply to multiply A by B, we do by multiplying rows of A by columns of B. And in particular, the entry of AB in the ith row, get slightly abstract here. The entry of AB in the ith row in jth column is the number that you get by multiplying the ith row of A by the jth column of B. So if I have these two matrices and I can multiply them, their product, AB, is a new matrix, so it has rows and columns. And to find the entry in its ith row and jth column, I just go to the ith row of A and I multiply that by the jth column of B, which is exactly what we did in that last example. You know, to find the thing in the second row of first column, I took the second row of A times the first column of B. That's what we want to do. Okay. Before we do another example, I want to highlight something on here, which is the dimensions. Notice this number n is the same as this number n. Those numbers need to be the same. So the guy on the left, this right number needs to be the same as the guys on the right left number. Let me say this a better way. If I'm multiplying two matrices A and B, A has to have the same number of columns as B does row. So I'm running out of room on my board, so maybe I'll sort of erase here in a second and write this neatly on the board. But for dimension reasons, we need to have the number of columns here match up with the number of rows. This is exactly like the same reason that to multiply a row and a column vector, they have to have the same number of entries. If these numbers don't match up, then I kind of just run out of stuff to pair up, and it doesn't make any sense anymore to multiply them. So let me write that up here. If A is m by n and B is, let's say, like some different numbers, k times by L, so these are two different matrices, then if n does not equal k, AB is undefined. Not defined, undefined. Opposite of that. So again, if the number of columns is not the same as the number of rows between these two matrices, then this matrix multiplication just doesn't even make sense. Say it's undefined. Because, for example, if I were to take A is this matrix, let's do 1, 2, 3, 4. And so this has 2 columns. And let's take this other matrix, 1, 2, 3, 4, 5, 6. So this is a 2 by 2, and this is a 3 by 2. So notice I have these guys are taking the place of n and k up here. They don't match. These are different. So if I try to multiply, you know, if I tried to take like the first row times this first column, well, I have 1, 2. Oh, I ran out of things to pair up. I can't pair anything up with this 5, for example. So I can't multiply this row and this column because they're just different sizes. They have different dimensions. So it makes no sense to multiply them. So this is undefined, because the number of columns of the first thing was not the same as the number of rows of the second thing. Okay. So that's very important. Again, you're going to have, there'll be a bunch of exercises on the activity where you're asked, here are some matrices. Is this matrix multiplication even defined? So you want to think about that. And it's very important to recognize when it's not defined. Because if it's not defined, you don't have to do it. Save yourself some work. All right. Let's see some more examples where this does make sense. I guess I'll pause again and ask, are there any questions? Another one of those days where I talk a lot. Okay. Let's see some more examples where this is defined to get a better feel for how it works. And then there will be a couple special properties that I want to talk about, and then we'll probably be about done with talking. Go to the activity. I don't know. Here's another example. How about 1, 0, negative 3, 4, 2. And here. So we'll multiply these two matrices. Mark up my markers everywhere. Here are these two matrices. Let's multiply them. So the first thing I would ask is this defined? And the answer is yes, because if we notice, this is a 2 by 3, and this is a 3 by 2. And those numbers are the same. So this is going to be defined. So we can go ahead and proceed. So how does this work? Well, again, I'll just remind you. Oh, maybe I should tell you as a side note.